This video should help you to be able to answer the last few questions in your booklet to do with log histograms. So the first example there, number 12, is looking at weight of different mammals. And you can see that the range of weights is very large. So there's the smallest animal is 0.4 of a kilo, and the largest animal is 70,000 kilos. So it's almost impossible when you've got a range that big to be able to sketch a normal histogram with that kind of data. So by taking the log of each of those values, we can compress the graph into a much, much smaller scale. So just to revise quickly on how to take a log on the calculator, you can see there I've entered the 10 values into my calculator and called the heading on the column weight. So then I want to get the calculator to take the log of each of those weights. So I've used another name on the next column just called log weight, and in the formula little cell there, I'm going to tell the calculator to do the calculation for all of those 10 values in one go. So I come into the formula cell there and I hit equals, and it then knows I'm going to make some kind of a formula in there, and I want to then put in log. Our scale is always going to be log base 10, and the name of the list of data that I want to take the log of is weight. So I type in the word weight, it goes bold. When I hit enter, it does all 10 of those log values for me. And you can see I've just written those onto my document there right next to the weights. I've got the log of each of those values. So now you can probably see that rather than the range being from 0.4 to 70,000, the range now only sort of goes between -1 to 5. So I've managed to compress that axis way, way, way smaller than it was before. So then all I do is I look through my log weights and I figure out in each interval for that log weight graph how many values fall in that interval. So I have got one value that's a negative value, -0.4, and that value falls between -1 and 0. So there's a frequency of one value that falls in that first interval. In the second interval, from 0 to 1, what I'm looking for in that interval is any of those values there that start with a 0 point something. And you can see I've got 0.95 and 0.60. So there's two values starting with a 0. The next interval is from 1 to less than 2. So what I'm effectively looking for there in my list of values, how many values start with 1 point something. Okay, they've got to be between 1.0 and 1.99 basically. So there's 3 values that start with a 1 point something. There's 3 values that start with a 2 point something for the next interval. There's no values that start with 3 point anything. And there's one value that is 4.85. So that's in that 4 to less than 5 category. So I have accounted there for all my 10 values, and then I can put those onto a frequency table, frequency histogram, I should say. So when it's asking me to draw a log scale histogram with class intervals of width 1, it just means each one of those intervals on my histogram, the unit size in the step from one group to the next is 1. So really all that is saying on the log histogram, for example, if there's a 0 there, it means that is the power that you put on a 10. So it's 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on and so on and so on. So hopefully that makes sense. So as we continue to move on with the questions there, again, we're looking at log histogram, slightly different little histogram. It's a little scatter plot almost. It has the weights there of 5 different animals. and they're plotted against a log scale. So really the bottom scale of that axis, where there's a 0, a 1, a 2, a 3, 4, 5, it basically means that the value on the bottom of that graph is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so on and so on. We are trying to put the gorilla's weight onto that histogram, and we know that the gorilla weighs 200 kilograms. So on my graph bottom scale, I have 10, I have 100, and I have 1,000, and I know that 207 falls somewhere between 100 and 1,000. So I know that that value for the gorilla falls somewhere between the 2 and the 3 on that scale. I don't have to be too accurate, but I know it falls between 2 and 3, between 100 and 1,000. So somewhere on that graph, if I can make my pen work here, on the graph, in between 2 and 3 somewhere would be somewhere here on that graph. So 207 is going to have a little power, 10 to the power of something. It's going to be bigger than 2, but it's going to be smaller than 3 to make a number that's 207, because what I'm really trying to do is fit a number in here somewhere. So I know that that gorilla, being 207 kilos, falls somewhere between the jaguar and the horse, which is D. So hopefully that makes sense. Again, with this one, speeds of different cars, so quite a large range of values again, between 34,000 metres per hour, what is it in speed? Metres per hour, miles per hour maybe, and a space shuttle that's going 28 million metres per hour. So quite a big range there, very difficult to put that sort of data onto a normal histogram. So we're putting log base 10 scale on that. And when you put those 5 values into your calculator, calculate the log of all of those different values. We're looking for the cheetah's top speed, which is the third one on the list there, so 64,000. You can see there that the log value for the cheetah's speed is 4.81. So that would be D. Okay, next question. So these two relate to this one bit of information here. So again, we've got different flow rates, cubic meters per second, that's flowing through different waterfalls there. And the two that we're interested in, for number 16, we're interested in Niagara Falls, which is the second value. And for number 17, we're interested in Victoria Falls. And both of these things are asking us to use a log scale and calculate basically the log of each of those two values. So if you see on the right-hand side there, the Niagara Falls is the second one on the list. So 3.38 would be Niagara Falls. That would be A. And then Victoria Falls is the first one on the list, which would round up to 3.04, which is B. So really your calculator's doing 99% of the work here. The very final question is number 15. And again, this is talking about capacities of different dams. Again, it's another little scatter plot, a bit like the weights of the animals. And they're, again, relying on your knowledge of the scales on log base 10. So 0 meaning 10 to the power of 0. This relates to a 1. 10 to the power of 1, this little one relates to 10. 10 to the power of 2, this relates to 100, 1,000, 10,000, 100,000 is this one, 10 to the power of 5, 100,000, and 10 to the power of 6, this one relates to 1 million. So basically by using that scale with the logarithm scale, we are able to basically fit between 1 to 1,000,000 on a scale that's only got 6 little ticks on it. Much easier to fit on a page. So the first question relating to this one is Thomson Dam. So when we look where the dot is for Thomson Dam, it is this one. 10 to the power of 6 relates to 1,000,000 megalitres, so B. Okay. Sugarloaf Dam, when we look for that one, if we have a look, Sugarloaf is the top dam. That dot there relates to Sugarloaf, which relates down here to the power 5. So 10 to the power of 5 would be 100,000, A. And then Sylvan Dam is the middle dot there, and you can see it relates to this one here. And that is also, it's a little bit, I don't think that's quite underneath the 5 unless I'm going cross-eyed. I think that's sort of somewhere here in between 4 point something. So what we know then is that if it was 10 to the power of 4, it would be 10,000. If it's 10 to the power of 5, it would be 100,000. So we're looking for something in between 10,000 and 100,000 for that dam. So D. So hopefully those few questions make sense. The main skill, I guess, is being able to make your calculator calculate all the logs for you, and then to be able to switch between a logarithm and a normal number. So when we're talking logarithm, we're just talking power of 10. When I'm talking normal number, I would say calculate that by going 10 to the power of whatever the logarithm is.